Hello, everybody. Thank you for joining us here today. My name is Kevin Waters. Work with KMW Technology. We are a search professional services consulting company based out of Boston. Been a long-time contributor to Solr and enthusiast about all sorts of technologies. I wanted to kind of take the time today to share with you a couple open source projects that I've been working with. And I think that they kind of are building a pretty compelling set of technology as this technology mashup here that we're going to show off. So what are we actually going to show today? What we obviously want to talk about is this life-sized humanoid 3D printed robot that is standing in front of you. We're going to teach this robot to recognize people by making an introduction. And just as humans meet each other and are introduced to each other, we should be able to teach our robots to do the same sort of thing. By exploring a lot of these open source technologies, I hope to simplify some of the barriers of the human-computer, human-robot interaction. So a little agenda, we're going to do a little introduction. We're going to talk about the InMoov. We'll talk about the open source project, MyRobotLab. And then we're going to go into some of the cognitive capabilities and the general anatomy of a cognitive robot. And if time permits, at the end, we'll do a little demo with some Q&A. So as I mentioned, I'm founder of KMW Technology. We have been doing search stuff for almost a decade at this point, and serves a lot of clients. And we've been seeing that there's a bigger sort of desire from our clients to start getting into some artificial intelligence technologies. And I've been using this MyRobotLab project to help further my understanding and explore these technologies. We do a lot of stuff around NLU and NLP and connectors and pipelines. That's the bread and butter of what we do. But I wanted to show you some of what I consider to be cutting edge. So, how did I get here? I guess it's just a desire to explore and try to do things to see whether or not you can. And I got involved with the sort of maker movement, which, if you don't know about it, there's this thing called a maker fair. Happens in about 190 different countries around the world, where people get to show off, their 12-foot tall bunny rabbit that's made out of dryer lint and things like 3D printed humanoid robots. I've always had a sort of passion for robotics, data, information retrieval, search, and now artificial intelligence. Some of the things that I've done with this robot, I've actually traveled a few places around the world, one of which was the Red Hat Summit a couple years back, where this guy was up on stage in front of about 5,000 people, and we were talking about the Robots for Good project, which was a project that was started by a company in the UK called Weaveover, and what they did with it was they actually took one of these robots, used telepresence so that children in the hospital could actually put on an Oculus Rift and look out of the head of the robot and kind of experience what it was like to be outside of their hospital bed and go around in a zoo, for example, to experience the real world, all without leaving the care of the hospital. So this guy was up on stage. I was terrified because I was sitting in the audience with a laptop and saying, don't pay any attention to the man behind the laptop. But he performed great, and he did his little song and dance for everybody. And up on the big screen there, you actually saw the stereoscopic feed coming directly out of the head of the robot. Fun project. So I would like to introduce this robot, but I will let him do it instead.
Hello, my name is Harry. I am the first life-size humanoid robot you can 3D print and animate.
Is that it? Hack not received. All right, the Arduino is disconnected. Well, as he decides whether or not he's going to come back online, we'll continue talking about him. So he was started and built in 2014.
I was built by Kevin Waters.
Okay. There's two Arduinos that control all the servo motors. There's a Raspberry Pi that's running the software. And unfortunately, when the voltage gets a little bit too low, the Raspberry Pis lose connection, which I think is what happened. There's two cameras that are in the robot's head. and it allows it to see. It's a stereoscopic vision. If you want, you can put on like an Oculus Rift and see through the head of the robot, as I talked about. We've integrated a lot of different technologies for speech recognition, speech synthesis, and most importantly, one of the things I'm going to talk about here in a little bit more detail is the fact that we've actually embedded a Solr instance in the robot, and that Solr instance is actually going to record his memories and give robots memories. So the robot itself is called the InMoov. This was an open source project started by Gael Langevin. He's a French sculptor and model maker. He began building this in about 2012, where he was commissioned to do a robotic hand for a photo shoot. That client never paid him, so he decided to open source it, and it was subsequently picked up by Bionico and Enable, which are some open source projects that 3D print prosthesis for amputees. I'd say there's probably at least about 500 of these around the world at this point. And just to comment on Gael, he's a very big proponent of open source and really believes in the democratization of artificial intelligence. I guess it takes a world to raise a robot, and we're all kind of trying to contribute our small little piece. The software that powers it is called MyRobotLab, and I, for one, welcome our new robotic overlords. It is started by Greg Perry, who's sitting in the audience here, from Portland, Oregon. It's a Java-based open source framework that have kind of what we call it Borging in technologies. I think we've integrated about 100 different open source projects at least. Each one brings a little piece of technology to the platform, a piece of functionality. MyRobotLab, in its essence, is a service-oriented architecture that can publish and subscribe to data, and you can kind of script all that stuff and do all your wiring in Python if you want to script things. Multi-platform, runs on Windows, Linux, Mac. Check it out on GitHub. What I wanted to talk about is how do we make this robot smart? How do we make it so that it can recognize people, interact with them? What are some of those challenges? Where do we want to take this going forward? How do we get this robot to understand and interact with people in a meaningful sort of way? We'll talk about the sorts of tools that exist to do that, how we can wire those together, and to actually see how we can interact with this robot, preferably without a keyboard. We'd like to be able to teach the robot about new things and hopefully make it cognitive and open source. So when I was thinking about how to piece together technologies, I wanted to focus on making something rather anthropomorphic. So I really kind of focused on what we think we understand about the human mind and our senses. That is that we have hearing, we can speak, we can reason, we can see, we can remember, and we can learn from our memories. And we have different technologies that can power each one of those key points. So if you think about it, all of these open source technologies are available for us. It's just a matter of being able to integrate them and put them together and actually make them do something that yields an emergent behavior from the robot. So at its core, for all of its memory and information retrieval, there is Solr. And because it is a service-oriented architecture, we have the Solr integration with an embedded Solr index that can wire itself in to all of the published and subscribed endpoints of all the services within MyRobotLab, so it can record and play back all of the data effectively that's passing through the nervous system of the robot. That becomes very, very powerful, not only for like debugging and performance tuning to understand how many messages are being sent from the vision processing service, what's being heard, what's being said, and how is it moving. So we'll talk about the hearing part, because speech recognition is definitely one of those areas that is advancing very rapidly because of artificial intelligence. Originally, the only open source recognition that we had was CMU Sphinx. Carnegie Mellon open sourced it. It was a very fixed grammar, only supported English. It couldn't recognize any words that didn't exist already in its training set. It was functional, but the accuracy on it was relatively horrible. So we actually had to put additional logic in that would say, "Did you say yes?" And you actually had to confirm that it actually understood you. We went out looking for other options, and kind of the best one that we found was Google Webkit speech recognition. If anybody has used it, it's basically the same speech recognition on the Android phone. It's built into Google Chrome, so we can access it through the web user interface using an AngularJS user interface in MyRobotLab. Nice thing is this supports about 60 different languages and different dialects. Downside is you have to be connected, and the great big Google in the sky is listening to anything that somebody says to the robot. So that's hearing. We should talk about speech now. We have speech synthesis. I'm not exactly sure how many different speech synthesis packages there are at this point. I think we have maybe 7 or 8 of them. MaryTTS, an open source one, Java-based. I think it was started in Germany. Decent connections, quality in terms of speech. A bunch of different voices you can choose that handle different languages. So you choose the correct speech model for the language that you want it to speak in. Mycroft AI, Local Speech, FreeTTS, Festival, these are all sort of like command line tools that allow us to pass it text. It generates an MP3. We cache that, and we can play that MP3 back. There's some online ones, Natural Reader, Acapella Speech. Very good quality. Again, requires internet connection. Amazon Polly is the same one that's used in the Alexa, if I'm not mistaken. So that's more of a commercial one. If you have an API key, you can use it. So natural language understanding is pretty important. People are going to interact with this robot. They're going to speak to it. So I looked back in the annals of history and found a technology called AIML, which I actually discovered close to 20 years ago. And AIML, I think a lot of people think of it as being very primitive, very, not like super fancy, but at the end of the day it works. It was designed in 1995 by Richard Wallace. It's a case-based reasoning. It's an XML markup language that uses recursion to break down an utterance, effectively applying anti-phrasing. And then once you've done all of that, you have the base thing that the person has their intent, and then you can reply with the response. There's hundreds of thousands of them that are written in AIML. There's lots of chatbots. One of note is Mitsuku. Every year there is a Turing test, and the prize for the Turing test is called the Loebner Prize. And the current winner of the Loebner Prize, the most human-like robot or chatbot, is called Mitsuku. And so Mitsuku is an AIML based.
I was printed out on a 3D printer.
Oh, yeah? He was printed on a 3D printer. Okay, so Program AB by itself is a reference implementation of an AIML interpreter. It was open source. I think it's a GPL license. So I took that code. It was kind of just like a bunch of Java code, refactored it, so now it's Maven-based. We updated the logging, so it does like proper log4j stuff. We improved its ability to load AIML, so it's about 40 times faster. We kind of extended it so that we can hook various functionalities. Like there's this ability to recursively call out and ask a robot on the internet rather than locally. And we kind of had a handler that we can integrate into there. Brought it up to speed so it supports UTF-8 all across the board. And Lucene tokenizers, now it supports Chinese, Japanese, and Korean because we integrated the Kuramoji Japanese tokenizer. You can look at these slides later. This is kind of like a little bit of an overview of what AIML looks like. The basic unit is a category that has a pattern and a template, and you can recurse, like something that somebody says greetings, you can recurse and respond for what it would have been for hi. It's not static. There is a learn tag in it, so you can actually tell the robot with categories like a pattern defined like this, learn that pie is yummy, and the robot will go through, add a category dynamically when you talk to it, so is that the next time you ask it, what is pie, it will respond yummy. In addition to that, we talked about the ability to call out to external services. So one of the things that we did in preparation for this conference is we set up a natural language understanding API that's running in Amazon right now. Behind the scenes, we used MyRobotLab to index and parse the Wikipedia dumps. We decomposed that into info triples to effectively index a knowledge graph. I don't know if Matt Holford's in the room here, but he did a lot of work on that. And what this allows us to do is create highly precise queries to retrieve very specific information to answer questions like, what is the population of Montreal? Or where is Boston? Or who is Albert Einstein? when we originally asked it who is Albert Einstein, its first response was a famous hydraulic engineer. Relevancy matters. So there is a guy named Hans Albert Einstein who was a great hydraulic engineer, not the one I was looking for. Wikimedia also publishes their views on like the page counts. So we took that information and used it as like a static boost on the documents and fixed the relevancy. So the next time after we did that, we asked it, who's Albert Einstein? And it started talking about relativity. So chatting with robots fun, responses, using Wikipedia, give it a baseline of general intelligence and information that it can call upon. What I think is more interesting is on computer vision. There is a fantastic project called Java CPP Presets, started by this guy Samuel Audette, and he effectively created a fantastic binding to not only OpenCV, the computer vision library, but TensorFlow and like, I don't know, 30 or 40 other like C-based libraries, because when you really get into a lot of this like heavy number crunching, you want to do it in C or you want to do it on a GPU. And these projects here are nice because they actually provide Maven dependencies. If you want to do this on Windows or Linux, 32-bit, 64-bit, even some ARM platforms, if you're into that thing, then you can actually just pull it in as a Maven dependency and not have to worry about it. Greatly simplifies like dealing with the J and I barrier. So in MyRobotLab, we've integrated Java CV and OpenCV and created a video processing pipeline with frame grabbers. It grabs images from the camera, passes it through a sequence of filters. Each filter is going to apply some sort of heuristic or logic or algorithm from Java CV to enhance the metadata, extract features, classify the image. We'll talk more about that a little bit later on. And then there's the question of memory, right? Because it's one thing to see things, but it's another thing entirely to be able to remember them. So as I mentioned before, there is an integration of an embedded Solr instance within MyRobotLab. And what it's able to do is attach to all of the services that are publishing data. It can take that information, store it in a Solr index, where then you can kind of query for it and get that information back so it can recall what it said, what it's heard, what it's seen. We use a couple key things in Solr. In particular, there's a binary field, and binary fields allow us to store binary data. So we actually take the video frames, the images from the cameras, we store them in a binary field along with the metadata of the global state of the robot. So if it knows that it's learning who Gus is, for example, then as those documents and those frames are saved from the camera into the Solr index, they're also labeled as being Gus. So it's kind of nice because in addition to like very targeted things like that we can do, you can use it just to attach to all of the information that's flowing through the nervous system of the robot, for lack of a better way to put it. Take that, index it, search it, facet it, get a sense of how many times was the on OpenCV data method called. Take a look at my data, explore the sort of synapses, if you will, of what's happening in the robot. What labels has it learned about? What services are publishing data? And things like that. So it's a very primitive, like swing-based UI. I'm almost a little embarrassed to show this, but at least it allows me to see the data from the embedded Solr instance. Which brings me to the next part, which is once you have memories, it's good if you do something with those, and that's where learning, and in particular deep learning, comes in. So we integrated Deep Learning for J. Deep Learning for J is an open source Java-based neural network and artificial intelligence framework for building and training either convolutional neural networks, recurrent neural networks, LSTM networks. We'll talk about some of those a little bit more. It also has a lot of what are called pre-trained models that you can use, and they call this a model zoo. So open source models that have been trained have been contributed either by researchers or whatever to the open source world, and we can actually take those models, whether or not they were trained in TensorFlow or Caffe or whatever, we can actually load them up in Deep Learning for J and evaluate them. As far as I can tell, Deep Learning for J is kind of the only game in town when it comes to Java-based deep learning. Under the covers, it uses a library called ND4J. ND4J is based on that Java CPP project that I talked about, and it effectively is modeled after the numerical library in Python called NumPy. or NumPy, depending on what you call it. So if you're used to doing deep learning with Python and you're used to using NumPy, ND4J is very similar. So it's kind of all of the same concepts are there. So the important thing with deep learning is creating training data sets and validation data sets. Some of the challenges in doing that are understanding how many examples you have for each label or category, understanding how to randomly sample that. So what we actually do is we issue 3 queries against the embedded Solr index. The first query is to get the total hit count, and it puts a facet on the labels. So in that result set, not only do I get the entire total hit count of all of my training data, I also know per category how many examples I have. Once I have that information, I'm ready to select or randomly sample that data, which is where I use the random sort field. And by random sort, I mean deterministically random, so that I can make it do the exact same thing every time. So it's very random. And I can run a query with a random seed. I sort this result set ascending. I can take the first 80% of those results, paginating through those, a little bit of deep pagination there, so there's some work to sort out. And that generates a randomly sampled training data set. And it provides me all of the information, the binary data that was stored from OpenCV, along with the associated labels. Once I have that training data set, I do the same query against Solr, where I sort the random sort field descending and grab the top 20% of those results, and that gives my testing or holdout data set for doing the cross-validation of the model that was trained. I mentioned before a little bit about some of the models that exist in the open source world. VGG16 is, I think in 2014, it was the first runner-up for a competition that occurs every year called ILSRV, SVRC, sorry, which is the large-scale image recognition competition. There have been major advances because of convolutional neural networks in these competitions. Before, like, people were using convolutional neural networks to do this image recognition, it was very difficult for anybody to have anything that looked decent. And now we're starting to get models that produce 95% accuracy on 9,000 classes of objects. VGG16 is one of them. It's a 16-layer deep convolutional neural network. The input to it is a 224 by 224 color image. So you can imagine that those are all of the inputs of the neural network, one input per pixel of the image, if you will, and it propagates through and was trained on the ImageNet corpus for doing that. And that's one of the ones that's available in the DL4J model zoo. So the VGG16 model only provides you classification of an image. There's another model out there, which is created by an open source project called Darknet, called YOLO, and this stands for You Only Look Once. And YOLO basically will take one image at a time, and we're Solr people, one document at a time, and it will classify that out of the context of anything else. And what it does is it doesn't just provide you the classification, but it also provides you localization. And by that, it gives you a bounding box. So if you've seen examples of neural networks on YouTube videos or whatever it happens to be, where you see the bounding box and the percentage of what it thinks this is a person or a microwave or a wine glass or whatever it happens to be, more than likely you're looking at the YOLO model. It's pre-trained, also available as a pre-trained model. You can download it. Slightly larger input, 416 by 416 resolution input for that model. Let's just stop for a moment and just say training neural networks is computationally hard. It takes a long time to do it. If you wanted to train VGG16 from scratch, it's about 140 million parameters that you're going to have to optimize using gradient descent and backpropagation. That could take weeks on clusters of machines. I don't like to wait that long. There's a fantastic approach to do this called transfer learning. And what transfer learning does is it takes a model that was trained for one purpose, and you can retrain that model to fit another purpose. So even though this VGG16 model can classify 9,000 different things, I don't care that my office looks like a barber shop. I want it to recognize it as my office, right? So what we can actually do with transfer learning is we take these pre-trained models, we hold some number of those layers frozen for our training, we reconfigure the output layer to some new number of outputs, and we only train that new output layer. So instead of having to train 140 million parameters and do the gradient descent and backpropagation to train those, all I have to worry about is that last layer. Effectively, it's about 4,000 parameters per category that you would need to train on. So the great thing about this is that instead of taking 3 or 4 weeks to do your training, you apply transfer learning, and with a reasonable GPU, in 5 minutes and about 50 examples per category, you can spit out models that are 80+% accurate. So this takes us from needing server farms and dedicated clusters just to do our training to something that we can do in relative real time on like a laptop with a decent video card. So it's a technology mashup talk, so it wouldn't be proper without mashing up some neural networks, because let's put them together and see what happens. So one of the things that we've done with the robot is we've taken the YOLO model, and anytime it detects a person, we can crop that image, we can store just the cropped image of the person in the Solr index, and then transfer learn to subclassify that person using the VGG16 model. And some of this was inspired by Christine's work on comments on Solr 11838. I think Joel's in the audience. He had some comments on that as well. And I think as a Solr community, we're kind of looking at how maybe we can integrate deep learning for J and Solr a little bit deeper to do some things like this. Christine's work actually allows you to use the streaming expressions as a data set iterator. Unfortunately, I was running an embedded Solr instance, so we created a Solr data set iterator that can use the Solr J client and actually iterate the result sets to do our custom training. It's the mind. So this is Lloyd. He is not really functioning too well right now. We can restart him and maybe we can get him to move and shake a little bit more. So I'm going to turn him off and we'll reboot him. And in the meantime, I'll show a different demo on my laptop because it's not doing what I want right now. I should probably actually, before I jump into the demo, talk about some of the other things that we want to do going forward. So there's always new technologies out there. Working with MyRobotLab has inspired me to just browse through GitHub and see what's there. Begin trying these things out, downloading them, integrating them. There's like some neural networks out there, one called Deep Wave, which is very good for generating speech. In the keynote, they started talking about generative adversarial networks and stuff, and using neural networks to do what's called seek-to-seek or sequence-to-sequence simulation. And one of the neural networks that's really good at doing that is called an LSTM, long short-term memory neural network, that has a concept of like gated information. So it kind of has a little bit of memory associated with each node in the neural network. We're looking at like improving performance and stability for the software. Some of the next things we want to start looking at is what's called SLAM, which is simultaneous localization and mapping. So these autonomous vehicles need to build 3D spaces around them. Just going to call out that the current release of MyRobotLab is called Manticore. The next release that should be out before the end of the year is going to be called Nixie, and the release that will come up after that is called Ogre. I would encourage you to download it, try it out. If you don't like it, change it. Pull requests are very welcome. So enough of that plug. And let's see how he's doing. We can maybe start him up again. And one of the other things I wanted to kind of show here is running on my laptop, which is considerably more powerful than a Raspberry Pi. You can actually see the YOLO filter in action, classifying me as about 87% of a person. I think it's being generous. who do you see? Because we should be able to.
I see Gavin.
Very good. And just for kudos, let's see if it recognizes any of these other people. Who do you see?
Interlinked.
Who do you see? Who do you see?
Null.
Sorry, Joel. I guess you got deleted. Who do you
Interlinked.
Who do you see?
I see Joel.
Who do you see?
I see Joel.
No, that's not Joel. I'm not Eric. So one of the key things is that being able to train these things is a little bit challenging. Right now, there's a Solr index that has about 25 examples of everybody, at least that I've got printed out here, some of the Solr committers.
Interlinked.
So let's go ahead and see
Interlinked.
if we can't teach it to do a little bit better than that. So
Interlinked.
I'll grab, we can do some
Interlinked.
basic stuff like, his name is Eric. His name is Eric.
Learning Eric.
And what it's doing now is it knows that it's being introduced to Eric. The next 25 frames are being saved into the Solr index. Once it's done with that,
Interlinked. Done recording Eric.
thank you.
Interlinked.
Her name is Christine.
Learning Christine.
So what we're actually doing is we're using program AB to parse my natural language utterance to set the state of the records that are
Done
being
recording
indexed.
Christine.
Okay, so we won't go through the rest of them, but I will ask the robot to go ahead and apply
Interlinked.
transfer learning so you get a sense of how long this process actually takes.
Interlinked.
Build a person model. And because no tech talk would be complete without looking at some scrolling text in a debug window. But I do actually want to point out a couple things here. This right here is a printout of the structure of the VGG16 neural network. It's telling me how many inputs there are. It's telling me how many layers there are. What I want to call to attention is that the first 15 layers here are frozen, and it's only the last output layer, the prediction layer, that is the one that we're going to be training. As we scroll down a little bit further, it prints out the evaluation of the confusion matrix. So this is an evaluation for the number of times I predicted category X, what category was it actually, and it tells me what the accuracy, precision, recall, and F1 scores are for this. It's going through doing its iterators, and then the second pass through iterating this data. Now the cross-validation is telling me that this model, which is training 17 different people at the moment, is up to about 87% accuracy. As we scroll up a little bit, I do want to as it's going through this
Recompiling my visual cortex.
very good.
Interlinked.
And
Interlinked.
so we-
Interlinked. Interlinked.
and
Interlinked.
now it's saved that new model out and just in real time put it back online. I mean, could you imagine being able to train a neural network to recognize new objects within, I think it was only about 2 minutes there that it took us to do that. So let's
Interlinked.
ask it. Where is my mouse? Here we go. And of course, being able to ask, who do you see?
Interlinked.
Who do you see?
I see Christine.
Very good. Okay, so thank you very much, everybody, for your time. I think we have about 5 minutes left for questions.
Interlinked.
If anybody has any. Or did I make it so easy that we can do it?
Interlinked.
Did anybody see the new Blade Runner movie? Yeah. There was like a scene where the robot or the replicant is doing his baseline testing and he says the word interlinked about 1 million times. So it's just a little pop culture thing.
Interlinked.
Yeah.
So would you You mentioned your random sampling technique.
Yeah.
I'm just curious why you didn't just continuously mold random with different seeds.
So
Why do
you-
keep going deeper into the same seed?
So, I mean, there's only one data set, right? And we just want to get like a random sampling for all of the different categories in that. And by specifying the same random seed, you get a deterministic result set. So when I retrain the model the next time, we're going to see the same results. And one of the important things is I wanted to make sure that I completely separated the data that I use for training versus testing. Because if I train and test the model on the entire corpus, it will just memorize the corpus. And there are some approaches, one's called Dropout, where you take a neural network like this and you randomly just start deleting nodes out of the network and tell it to like try to adapt to it. And that's one of the approaches to making it a little bit more generalized. Anybody else?
I'm wondering if we're working together.
You want to stand? Because that's an interesting test, because it has never seen anything other than a photo of Christine. So, yeah.
And I'm wearing glasses, which the passport machine normally.
Who do you see?
I see Micaiah.
Try again without glasses.
Who do you see?
I see Micaiah.
Her name is Christine.
Learning Christine.
Yeah, that's it. Okay. So. No, it's safe. It's the wild, wild west these days, so I'm all for it. Anybody else? Yes.
One of the slides you're showing NLP and NLU.
Yes.
Between the two. Is there an NLU component?
So yeah, so on the NLP side, it's really NLP and NLU I'm kind of lumping both of those together in program AD with AI/ML, because what it's doing is it's processing the natural language to figure out what the intent is. So mapping whatever you said, whatever your utterance was, to a base intended action. So that's the natural language processing, and then the natural language understanding. And understanding is driving the utterance to the intent. And that's kind of where I'm lumping both of those together. There are like integrations and you talk about with like OpenNLP, so we can do like part of speech tagging, but that's all stuff for the document processing pipeline and connector framework in MyRobotLab, because I'm a search guy and that's what I added into it.
So you have an intent classification engine, and then you have a search engine. So when you say something, which goes, where does it go first? Does it go to the search engine first or to the intent?
Well, when you say something, right, it goes first to the ear, which hears it, speech recognition with Google Webkit speech recognition, and that's going to publish the fact that it heard something. And because the data is being published from the ear to other services like the chatbot in the head, the Solr instance is intercepting that signal and recording it. Does that make sense?
Yeah, but so you send it simultaneously to both Solr
Yes,
and
so it's a publish subscription sort of framework. So it's a service-oriented framework. Each service, whether or not it's a speech recognition service, the vision service, OpenCV, program AV service, they're publishing and subscribing data to each other. And we're just intercepting the messages that are passed and indexing those in Solr.
So the final output is what? From Solr or from the chatbot?
Solr is for memories, but the chatbot is actually what's responding to. Yeah. It does, yeah. So two responses to that, and hopefully one of them will answer your question. First response is that actually there's Oculus Rift support for MyRobotLab, so you can put on the Oculus and you can see out of the head, because there are two cameras with a little bit of, it's called an affine transform. We can translate and rotate the images to account for the interpupillary distance, so as that you actually achieve stereo convergence. And you have binocular vision with depth perception when you're doing that. That's one thing. The second answer that I'm going to give, which may be actually what you're asking about, is reconstructing 3D models from stereo cameras. And there is a probably like 30 or 40 different algorithms in OpenCV to do that. I haven't used them yet. Maybe if you want to make a pull request, I'd be happy to review it. At the moment, no. I think it would be very interesting to be able to, instead of using two-dimensional images for classification, to somehow figure out how to provide either a point cloud or a mesh, and use that as an input to a neural network for classification. I'm just speculating on how well that would work. I would have to think about it for a while. It's kind of an exciting possibility there. Okay, one last question. I think we're up to
Your
10.
AI ML, is that file from the
Yeah, everything that I've talked about here, 100% open source. 100%. I'll send you links to it and come up and I'll share with you those links.